Hello and welcome to the Chemistry Academy. In this video we're going to go over fertilisers in relation to the National 5 chemistry course. So there are a few things you need to know about fertilisers, which we'll go over first of all, and then we'll look at how we can make fertilisers on an industrial scale. So the whole point of fertilisers, and you have to be very careful with how you word this in any chemistry exams, because sometimes the wording, if you word it a slightly different way, you're not really getting the full point across. So the point in a fertiliser is to provide essential elements for plant growth. So a lot of the time people say fertilisers help plants to grow, which they do, but you have to be specific in how they do that. So they do that by providing the essential elements that the plant needs. The three essential elements for plant growth are nitrogen, phosphorus and potassium. So try and remember NPK. And those are the three elements that are essential for plant growth, so plants can't grow without those three elements. When we're making fertilisers, then we need to make sure that the fertiliser contains at least one of these essential elements. Of course, the more of these elements, the better. But it also needs to be soluble in water. So if you're trying to determine if something would be suitable as a fertiliser, it needs to meet these two criteria. So you can tell what elements are in it from its name normally. And then in order to tell if it would be soluble in water or not, you would just use the solubility table in your chemistry data booklet. So the big table with all the I's and the VS's in it. So you can look up the compound there and check that it is soluble. On the solubility side of things, not that it's often a thing you need to consider, but if something is too soluble, then that's not very good for the plants either, because it means that your substance is likely to get washed away quite easily if there's a lot of rainfall. So a decent amount of solubility, but not too soluble. So a bit of like a Goldilocks zone with that one, but it needs to be soluble. So if you get a question asking something isn't suitable as a fertiliser, it's probably because it's not soluble. So if you look it up in the solubilities table, you should see there's an I next to it, and therefore it can't be used, even though it might contain one or more of the essential elements for plant growth. In terms of how we then make fertilisers, so really the final stage where you are producing a fertiliser is a neutralisation reaction. So there are a couple of industrial processes we're going to go through after this that lead you to then making a fertiliser. But at the end of the day, really it is the neutralisation that is making the fertiliser. So fertilisers are essentially just salts that contain one or more of the essential elements for plant growth. So when we're making fertilisers, we generally take an acid and a base, and we end up forming the salt, which is what then gets used as the fertiliser, and of course water gets made as well. Here's some examples of acids and bases that could be used to produce a fertiliser. So we could have nitric acid that contains the essential element nitrogen. We also have ammonia as a base, and we'll talk a bit more about ammonia after we go through this. But ammonia also contains nitrogen, and that would produce a salt called ammonium nitrate, which could be used as a fertiliser because it is soluble in water and it contains one of the essential elements for plant growth. It contains nitrogen. We could also have, as an example, phosphoric acid. So phosphoric acid contains phosphorus, and we could react that with potassium hydroxide, which contains potassium, and that would give us the salt potassium phosphate. If you need some more help with naming salts, then you might want to go back and watch my acids and bases video, because I do a lot of naming salts in that. So the potassium phosphate would be the fertiliser in this case. Contains two of the essential elements for plant growth, and it is also soluble in water, so it would be suitable as a fertiliser. Other things we could do, just as some other examples, we could use hydrochloric acid, which is HCl. Hydrochloric acid itself doesn't have one of the essential elements of plant growth, for plant growth, but you could react it with a base that does contain one of those elements. So we could react it with like potassium oxide, which is K2O. If we reacted it with potassium oxide, we would make potassium chloride as the salt if we've used hydrochloric acid. And potassium chloride is also soluble in water, so that'd be KCl, and because it's aqueous, so it has one of the essential elements for plant growth and it's soluble, so it could be used as a fertiliser. What we need to watch out for would be an example like this. So let's say we used phosphoric acid, and let's say we reacted it with magnesium hydroxide. So that's just a base. It doesn't have any of the essential elements for plant growth in it, but it is a base that we could produce a salt with. So that'd be MgOH2. The salt we would make from that would be magnesium phosphate. But if we were to look up magnesium phosphate in the solubilities table, we would find it's actually insoluble in water. So that would actually end up being a solid precipitate and it wouldn't redissolve in water, so we couldn't use it as a fertiliser. So even though it contains one of the essential elements for plant growth, it's not soluble, so it wouldn't actually be suitable. Our fertilisers are normally sold as in solid form. So we do often want to obtain dry samples of these salts. Now, because all the salts that are used as fertilisers are soluble, when you do produce them in your neutralisation reaction, they are dissolved in water. So to obtain a dry sample of them, we just need to use evaporation. We would evaporate off all the water that's produced, and then we would be left with our dry sample of our fertiliser. So that's just one other thing to remember. To obtain a dry sample, use evaporation. So what we'll do now is go on to look a bit more at ammonia, because you do get asked specifically questions about ammonia, and then we'll look at the two industrial processes involved in the production of fertilisers. But I just wanted to first of all go over what a fertiliser is and how we actually make the fertiliser itself before we look at the processes involved in the build up to that. So now going on to look at ammonia and the industrial processes that are used in the production of fertilisers. We start off with ammonia itself. So ammonia is a molecule that has the formula NH3, so it's made up of nitrogen and hydrogen, and this is what it looks like here. So it's got a trigonopyramidal structure as a covalent molecule. It is a small covalent molecule, therefore it has very weak attractions between its molecules, so it will be a gas at room temperature and pressure. So remember from when we did homologous series, we talked a little bit about attractions between molecules, intermolecular attractions, and the weaker they are, the more likely something is to be a gas at room temperature. So ammonia is a quite small molecule with relatively weak attractions between its molecules, so that is why it is a gas at room temperature. It will dissolve in water. It's very soluble in water, and it dissolves to give an alkaline solution. That alkaline solution it produces is called ammonium solution. So when ammonia gas dissolves in water, it produces ammonium solution, and ammonium is NH4 positive. So don't get confused between ammonia, which is NH3, and ammonium, which is NH4 positive. Okay, so they are slightly different. Because the ammonia dissolves in water to give an alkaline solution, there is a chemical test for ammonia in which it turns damp pH paper purple or blue. And that's because if the pH paper is damp, then there's water there for the ammonia to dissolve in, and it will dissolve to produce this alkaline ammonium solution. That's how we can tell that ammonia is being produced from a reaction, is by using damp pH paper and seeing if it turns purple. So that's really all you need to know about ammonia as a molecule. It's NH3, it's got a trigonopyramidal structure, it turns damp pH paper blue and purple because it readily dissolves in water to produce an alkaline solution. And that alkaline solution is known as ammonium solution. So then we've got how we actually make ammonia on an industrial scale. So ammonia is produced in this process called the Haber process. So the Haber process was invented round about like World War I times, World War II, and it's essentially a reaction where you take nitrogen gas and hydrogen gas and react them in order to make ammonia, which is NH3. Now this reaction though is reversible, it's a reversible reaction, so that's what that arrow going backwards and forwards means. Although we can produce ammonia, the ammonia will break back down into nitrogen and hydrogen again. So when you go on to take higher chemistry, you will learn a bit more about how we can produce more ammonia, even though it breaks back down again, but you don't need to know that for National 5, you just need to know that this symbol means it's a reversible reaction. There is a catalyst used in the Haber process. That catalyst is iron, and the catalyst just allows the reaction to be run at slightly lower temperatures and speeds up the reaction, as you know from doing your rates of reactions topic. That's what catalysts do. They speed up the reaction and allow reactions to be run at lower temperatures. So that helps in industrial processes because it means it costs a bit less, and it's also safer because there's less risk of explosion if there's not as much heating going on. The ammonia that's then made in the Haber process, and of course we're making the ammonia because we can use the ammonia as a base in order to make a fertiliser that contains nitrogen, one of the essential elements for plant growth. But we can also take the ammonia and use it in the Ostwald process to make nitric acid. Nitric acid would be an acid we could use to make a salt that contains one of the essential elements for plant growth, nitrogen. So the Haber process and the Ostwald process work together. The Haber process produces the ammonia that the Ostwald process needs to then go on to produce the nitric acid. Interesting story, the Ostwald process was actually developed before the Haber process existed. So Ostwald made up his process, but he actually couldn't run it on a large scale because he couldn't produce enough ammonia for it. So then Haber came along and made an industrial process for producing ammonia, and so then Ostwald was able to use his process on a large scale in order to, because Haber managed to find a way to produce a mass amount of ammonia. So yeah, it's just quite interesting that the second stage of this process was actually invented before what we're now classing as the first stage. So the Ostwald process, like I said, produces nitric acid. Ammonia is one of the reactants within that, and all that happens is ammonia gets reacted with air, specifically the oxygen that's in the air, and it produces nitrogen oxide gases, which we then dissolve in water to produce nitric acid. So if you remember from our acids and bases topics, when non-metal oxides dissolve in water, they produce acidic solutions, and that's exactly what's happening here. So we produce the nitrogen oxide gases, and then we just dissolve those in water to produce our acid. So sometimes you will be asked what gets added at the last stage of the Ostwald process. Just remember it's water, so it's just to dissolve the gases to produce the acidic solution. There's a catalyst used in this process as well. This time it's platinum as a catalyst. If you struggle to remember which one's which, you can actually use the alphabet to help you. So I comes after H in the alphabet, so it's iron with Haber, and P comes after O in the alphabet, so it's platinum with Ostwald. The Ostwald process is a very exothermic reaction, so we do need to heat the catalyst or heat the reaction to start off with, but once the reaction starts, we don't need to keep heating, and that's because it's very exothermic, so it self-heats, basically. So you can be asked about that sometimes as well, as why the Ostwald process only has to be heated at the start of the reaction, and it's just because it's very exothermic, so it will then self-heat once it's started. So that's it really for fertilisers, the essential elements for plant growth, what they are, the requirements for a fertiliser, the process of making a fertiliser through neutralisation reaction, and how to obtain a dry sample through use of evaporation, and then the processes involved in the production of ammonia and nitric acid that we can then take and use to go and make our fertilisers. So I hope you found that helpful. If you did, please give this video a like, don't forget to subscribe, and I'll see you again soon.